Yeah. Yeah. I don't do
He's
that.
growing it out.
All the way, Rachel. All the way.
He's gonna be real
Everyone that
awesome.
I
I'm gonna get
know
coffee by this.
is here.
Hey, Rachel.
Everyone. Even Professor. I literally ran into somebody from my chemistry class group in the hall on the way here. I guess
Good. How are
it's the
you?
year before me. She's graduating this
Realize that you were stealing my work.
last year.
Oh, I'm.
It's ridiculous.
I have to update it. I have to go full members.
Yeah.
Everything good?
Yeah, I'm taking quantum this semester, doing directed independent research, Astronomy Society.
Yeah.
All right, thanks everyone for coming. We're gonna get started. Make sure no one invites the fire marshal. So thanks everyone for coming to the colloquium, and I'm super happy that Dorian let us be open today. Otherwise, I would have missed this really awesome chance to hear this talk. I'd like to introduce Dr. Michael Johnson, not our Dean of College of Sciences, Michael Johnson. It's Dr. Michael Johnson from the Smithsonian Astrophysical Observatory, and we're very delighted that he agreed to come down here to give us a talk. I know many of you have heard about the Event Horizon Telescope and M87 and the billions of solar masses of black hole. So we're going to hear a talk from Dr. Johnson about that very topic. So I'll let him speak.
Well, thank you so much, and thanks for the invitation to come visit your program, meet some of the students and faculty. It really sounds like you have a special place here, and that's fantastic. First of all, can you all hear me okay? Good, okay. Well, so today I just want to tell you a little about the Event Horizon Telescope results. Walk you through what they really mean. Beyond just a news headline or something like that, but actually how we got them and the process of doing that. And then also give you a sense of what's next. What are the next big discoveries that might be just around the corner. So to put this in context, I really like this movie, and what's special about this movie is that everything you see is an actual astronomy observation. So here, tucked between the constellations of Virgo and Leo, there's this massive elliptical galaxy called M87. This galaxy is about 50 million light years away, which means that even with the best optical telescopes we have, like the Hubble Space Telescope, all you see is this ball of stars with a faint jet extending from it. So this is an actual Hubble image. Now with radio interferometry, you can actually zoom in and you can see higher resolution features. You have this booming jet. And as you look at higher and higher frequencies, the jet becomes translucent, so you can peer deeper and deeper into its heart. Until you get to 230 gigahertz, and this is the image that we published with the Event Horizon Telescope in April. So again, there are some things that I just love about this movie. And the first is that you see that the Event Horizon Telescope, it was not just a one-off thing. This is building on decades of work, just steadily marching towards the centers of these galaxies. The second thing that you see from this movie is that nature didn't step in at any scale and say, black holes can't form. And that's what physicists thought after black holes were proposed in the early 1900s. They said, oh yeah, that's fine that your math tells you that, but surely nature steps in and something will stop this singularity from forming. And not so. We can actually now see all the way down to the heart and see this black hole, which has about 6.5 billion times the mass of the sun. Okay, so to put this in context, if the Earth were compressed down small enough to be a black hole, it would be about an inch across. You could hold it on your finger. This black hole would engulf our solar system. Okay, so this is an absolute monster. Even as black holes and galaxies go, this is among the most massive ever discovered. So what we think we're seeing here is actually pretty simple. We think that there's basically this black hole sitting in a bath of hot plasma. And this plasma is at tens or hundreds of billions of degrees. And so the black hole has a few effects on this plasma. One is that its gravity is so strong that photons are bent around it. And the second is that it's blocking photons behind it, and photons in front of it are trapped. And so the net effect of this is this glowing ring on the sky. So what I'd like to do today is just walk you through, how did we make this image? What does it mean for physics? And how do we make it better? So the first thing is the Event Horizon Telescope. So the Event Horizon Telescope is not one telescope, but it's actually a collection of telescopes all over the world. Okay, so what's special about this is these were all facilities operating independently, studying the sky in their own ways, individually. And what we did in the Event Horizon Telescope is that we went to each facility and we installed some specialized equipment. So one thing is atomic clocks. And this allows the telescopes to become perfectly synchronized with each other, even when separated by these large distances. The second thing that we installed is extremely high-speed recording equipment. So we record data rates now at EHT sites of about 8 gigabytes per second at every telescope. So over the course of a week-long observation, we're now collecting something like 5 or 10 petabytes of data. It's hard to really wrap your minds around what huge amount of data that is, but this is not things that we're emailing around. We're actually shipping, truckloads of disks. It's a lot of information. Now, once you join all of these telescopes together as an interferometer, we get images like this, and you can see this little circle in the lower right. That's the point spread function of our instrument, or the beam. That's our resolution element. So you can see we get this blurry image of a black hole. It's not blurry because the black hole is blurry. It's blurry because we're pushing our instrument to its absolute extreme. So this is, in the language of physics, this is the diffraction limit of the telescope. So we're observing at 230 gigahertz, and that's a wavelength of light of about 1 millimeter. So it turns out that this technique has been developed for a long time, connecting telescopes in different places. It's called Very Long Baseline Interferometry, or VLBI. But the thing that's special about the EHT is that we push this to higher frequencies than had ever been done before. So the next highest frequency is 86 gigahertz. So we're almost a factor of 3 better than anything that ever came before. Now, in terms of the timeline, in 2017, we took the data that led to this image. So this was a really special year for the project. We've actually been taking data since about 2007. And what we're doing is just slowly adding sites, adding the new equipment, bringing them into the array. Sometimes the sites that we equipped would close, so there was a lot of back and forth there. In 2017, we did something special, which was to bring ALMA into the array. So ALMA is actually an array of telescopes in its own right. It's got something like 60 telescopes all tucked together on this plateau in Chile. And what we do is we combine the signals from all of those to synthesize one enormous aperture. So it's as though they're all acting as one telescope that's something like 70 meters in diameter, which is huge for these telescopes that have to be observing at these short wavelengths of 1 millimeter. So we brought ALMA in, and more than that, we brought in LMT, which is a telescope in Mexico for the first time, and also this telescope Pico Veleta, which is in Spain, and the South Pole Telescope. And this is what allowed us to make images for the first time. But we're not stopping there. In 2018, we actually added a telescope in Greenland. So this is data we've taken, but it hasn't been published yet. Greenland is great for M87. So M87 is the northern source, so this is going to make our images even better. And in 2020, this campaign could be another turning point for the project. We're actually adding 2 new telescopes. One at Kitt Peak in Arizona, and one is called NOEMA in France. And you'll see in a minute why even adding 1 telescope can be profoundly important. So here's the array, but how does it work? How do you actually make a picture from all this data? So to understand that, I actually wanted to turn this sort of a whimsical example where we can draw some inspiration from ducks. So here's the ducks. They run into the pond and they start kicking their feet furiously. So they're kicking away, and the water near the ducks is stirred up and turbulent and irregular. Well, what you'll see further away, at strangely low resolution, is these outward propagating wavefronts from the ducks. So they're nice, coherent propagating wavefronts. So near the ducks is all random and irregular, but then that gets stretched out the further and further away you get from the ducks, and so you get these nice, smooth propagating waves. So to understand how the EHT works, I want you to think about a toy problem. And here's the problem. You're on the boundary of the pond, and you're blindfolded, and you can't hear anything we'll say. And your problem is, tell me where the ducks are splashing. You have to tell me where they are around the pond, and all you get to do is you can feel the water sloshing up and down against your feet. So the question is the information and where the ducks are contained in that sloshing pattern? And if so, how do you recover that? So it's a pretty simple problem. So to understand the solution, let's abstract away a little bit more. Here we have some ducks in a pond. On the left, these are ducks that are close together. On the right, they're far apart. So let's let those ducks on the left splash first. So they start kicking their feet, stirring up the water. You can see near the ducks, it's very random, and further away, you see these coherent wave fronts. And just imagine that you're sitting on the edge of the pond there, just feeling the water lap up and down against your feet. So that's the ducks that are close together. Ducks that are far apart, they do the same thing. They start kicking. We see the same qualitative pictures. And we're just looking at the diffraction pattern of these ducks. And this is very similar to a two-slit experiment that you may have heard about in your classes. So what you'll see here is that these two pictures actually have some similarities and some striking differences. One is that the amplitude of the sloshing pattern is actually the same between the two cases. So the amplitude is just telling you how many ducks there are, but it actually doesn't tell you anything about where they're located on the pond, which means if you're by yourself on the edge of the pond, you know nothing about where the ducks are. This is like a telescope by itself, can only tell how bright an object is. However, the coherence length around the edge of the pond is quite different. So imagine that you're there with a friend, and what you're doing is you're actually comparing the two sloshing patterns that you both see. So when you and your friend are close to each other, you see the same pattern. As you move further and further apart, at some point it decouples, right? And you and your friend are seeing different patterns. So it turns out that distance that they have to move before you start seeing different patterns is much closer in the case of ducks that are spread out. And this can be formalized in the language of Fourier analysis, where each separation around the edge of the pond is actually sampling one spatial mode of the distribution of ducks in the pond. Okay, so, kind of a fun example. It sounds completely irrelevant, except it's actually quite similar to the problem of the EHT. So for the EHT, we don't have ducks in a pond, but what we have are electrons that are gyrating around magnetic fields at the source. So these things are zipping around magnetic fields, and they're spraying out synchrotron radiation, which is like electromagnetic ripples, just like the waves in the pond. Now, we're not sitting around the edge of the pond. What we do is we put telescopes as widely separated as possible, and these just measure the incident electromagnetic waves. And then after they're recording those waves, what we do is we correlate the signal between every pair of telescopes, just like you and your friend comparing the sloshing pattern. We're just comparing the sloshing pattern in the electromagnetic signature and seeing how similar it is with different telescope spacings. So then we turn that into a picture by doing this Fourier analysis, and this is a technique for forming images called synthesis imaging, which was pioneered by Martin Ryle, who got the Nobel Prize for it in 1974. So that's how interferometry works, but why would anyone ever do it? So it turns out there the answer is all about angular resolution. So for ordinary imaging, your angular resolution is just determined by the diffraction limit, lambda over d. So a few numbers, your human eye is observing at visible wavelengths, and it has a diameter of a centimeter or whatever it is. And that'll get you to an angular resolution of about an arc minute. Now, radio telescopes can be enormously larger than your eye. Here's Arecibo. And Arecibo has hundreds of meters of diameter. But it's observing at radio wavelengths, which are much longer wavelengths than visible wavelengths. And so it turns out radio telescopes, even the best ones in the world, have about the same resolution as your eyes. They're not good for high-resolution astronomy. Optical telescopes can, of course, have much larger apertures and observe at visible wavelengths, so they can be thousands of times better than your eyes, get down to about 50 milliarc seconds. Okay, so the magic of interferometry is that the resolution from your diffraction limit doesn't depend on how big any one telescope is. It depends on how far apart you can put them. But this comes with a price, and the price that you pay for this is that you're no longer forming images directly. So each pair of telescopes just samples one spatial frequency of the image. So one way to think about this is if the image were a song, every pair of baselines would just hear one note. So if you want to piece together the entire song or see the whole image, what you need are many different baselines, short and long, and many different orientations, and then you can combine all that information together to make a picture. So the EHT in 2017 had 7 telescopes that could see M87. 7 telescopes give you 21 baselines. So the EHT in 2017 heard 21 notes. That's not very many. And it turns out you can't make an image with 21 notes, or 21 spatial frequencies. But it turns out we have one more trick to play, and that's that we can make the Earth part of our instrument. So here's how that works. So again, each pair of telescopes measures just one spatial frequency. So on the left, we have a picture of the globe and 2 telescopes on it. Those are actual EHT sites. And on the right, we're just going to track where that spatial frequency lives. So that's these 2 dots. And it samples 2 because it's the same information going from one telescope to the other, or going from that guy back to the first. And the special thing is that as the Earth rotates, this projected baseline between the telescopes is changing. And so actually, every pair of telescopes on the globe can sample many different spatial frequencies of your image as you let it build up over the rotation of the Earth. So the extra trick that we play is we actually we assemble data from an entire night of observation, letting the Earth rotate as much as possible while the telescopes can still see the source. And then we take all of that information together and we feed it in to make a single image. And so this is called Earth rotation synthesis imaging. And this is the entirety of the data that the EHT records. Okay, so here's an example of a plot that you might see in one of our papers. And this looks very technical. Let's focus on this one on the right. So it's visibility amplitude versus baseline length. So baseline length now is easy. That's just, you take your telescopes and how far apart is the line between them. The y-axis is it's that measure of correlation we talked about. So a high value here just means that you and your friend on the pond are seeing the same sloshing pattern. And as it goes down, that means that you're seeing independent sloshing patterns. And so what we're seeing here is that as we go to longer baselines, we're starting to resolve the source. If it was a point source, then every baseline would see the same value. So this is telling us that the Event Horizon Telescope is resolving the image of M87. But the other aspect here that was really exciting to us, because we had this before we had images, right? This is just the raw data, is that it has this peculiar feature that it comes down very fast and then it bounces. And it comes back up and then goes down again. So it turns out that that is a characteristic signature of something like a ring. So here in gray is just the interferometric response of a thin ring. So this was tremendously exciting to us when we first saw it. But the problem is lots of things can give these types of bounces. It turns out a disk, a filled disk, can also give a bounce. And other things can give bounces, like 2-point sources that are offset from each other. So we knew that there was interesting structure here, but this definitely isn't enough information to say we've seen the shadow of a black hole or something like that. For that, we need imaging. Okay, so what makes imaging such a difficult problem? To understand that, you have to understand the context of the EHT. So with the EHT, we're trying to take a picture of something that's never been seen before, with measurements that are difficult to calibrate, and using an instrument that no one's ever used before. So the EHT, first of all, there's nothing on the sky that's ever been seen with interferometry at 1.3 millimeters. It's not just that we published the first image of a black hole with EHT. We published the first image with EHT. That is the first, we can't look at anything on the sky and say, oh yeah, that looks like what we got last year, therefore our instrument's working. Or we got the same thing that this other group got. Like, no one's ever seen anything on the sky at these wavelengths. So we're really flying blind here, and it's imperative that we make sure that nothing we do in this whole process is biasing our results. So how can we do that? This process, we actually divided then up into a few different steps. So the first step is that we wanted to do blind imaging comparisons. So the moment that EHT data were ready to be analyzed, we broke up our imaging efforts into 4 different teams. And at that moment, we said there's no communication among the teams. And then we wanted each team to take that data and make an image from it. Now, this isn't just something like, well, I have to pick my algorithm and run it through or something like that. There's a lot of sort of personal decisions that you make along the way. One team might say, we think this data is problematic and we're going to discard that. Another team might say, we are going to try this particular calibration procedure. Another team might say, I think the data are perfect and I'm just going to make an image with that assumption. Right? Each group had to make their own decisions about how to interpret the data, the imaging algorithms to use, and so forth. And we wanted to make sure that there wasn't any shared bias among all the different members of the EHT, so that we could really confirm that any structures that were there were things that we'd all stand behind. So after the data were distributed, each team had 7 weeks to work on the data, and then we all came together at a workshop in Cambridge, Massachusetts, to compare these results among the 4 teams. And this is what we got. So these are the 4 images, all produced with no communication whatsoever. And the thing I love about these is that, you know, they're different, right? It's not like we all converge to the exact same result. However, there's some clear features, right? Every single one of the reconstructions has a ring. The rings are all about 40 microarcseconds across, and the rings are all brighter on the bottom. Okay, these are the features that we trust. Everything else is still uncertain. So you can see that some of the groups, you know, this one has a little faint feature coming off here. In a traditional publication, maybe we publish that and we talk about maybe there's a jet there and we assign interpretation to it. But in this process, we see really it's not substantiated in the data. Other groups could make other decisions in which that type of feature goes away. So I think these types of images really give you a sense of the things that you can believe in the final images and the things that you can't. So here's all of us, you know, after seeing this first this is actually the average of those 4 images for the first time. And you know, this was a big moment for us. This was really the moment in the collaboration when we knew that we had this result. Before then, there was no guarantee that we could even make an image from the 2017 observations. This was really a culmination of that. And I just wanted to highlight the contributions of a few people, since I know there are a lot of students here. This is Andrew Shale. He was a Harvard graduate student who I worked with a lot. He's the lead developer of a new imaging library. So at the start of his PhD, he came in knowing nothing about this type of astronomy, and by the end, he wrote an imaging library from scratch that produced one of these images. We used 3 different imaging libraries. A second one is called Smiley. That was written by Kazuo Akiyama, who's now a Jansky Fellow at Haystack. He also wrote that from scratch as a graduate student. So 2 out of 3 libraries were written from scratch by graduate students. And the third is Katie Bowman, who I'm sure many of you know. She was a graduate student when she started working on the project, and she really led the synthetic data and blind testing design. She had a huge role in this project. So it's really, a lot of these techniques are completely new to how radio astronomy is done, and I think that's a testament to the involvement of these students who all played absolutely major roles. So at this point, what do we do? Right? You can't just pick your favorite image and publish it. How do we determine which image is correct? So for that, we turn to synthetic data. So what we did is we started with a set of simple toy models. So here's one's a uniform disk, one's a crescent, a filled disk, and a pair of doubles. And what we wanted to do is say we want an imaging algorithm that's reproducible. We want it to be scripted, you know, so that no human is fine-tuning the final results. And we want an imaging algorithm that would work in all of these cases. We don't want something that produces a ring when you give it data from a disk. So each of these was selected because they produced data that looked very similar to the EHT data. And on the bottom is a reconstruction with one of our algorithms where you can see how it does when it's handed data from this particular model. So then we scored each of our imaging algorithms. We ran imaging parameter surveys that allow basically a computer to try all the things you would normally do at your computer. You know, I'm going to change this knob, and I'm going to make that a little stronger, and I'm going to add this step. We explored hundreds of thousands of images in this way, and each one was scored on its ability to reconstruct these synthetic data. So in this case, the beauty of it is we know the ground truth. So we can say whether or not, we can objectively say whether or not the imaging algorithm is doing a good job. And so this was the way that we selected the final images that you see in the newspapers and so forth, was to do these parameter surveys with hundreds of thousands of images, and then just objectively say this is the parameter set that we're going to use for our final results. Now I mentioned earlier that that in VLBI, even one new site can be transformative. So I just want to give you an example of that with some of these imaging algorithms. So here's an example where I've trimmed away all of the data except a single baseline. So you could say, suppose that the EHT just had 2 sites. What would you be able to see? So 2 sites give you just this one spatial frequency, and it turns out with that, all you can really say is how big the thing on the sky is. You just get a big blob on the sky. So we can add another site. Now we have 3 sites, or 3 baselines, and this is along the same direction, so you get a little more structure along that direction. That's enough to kind of separate this into 2 blobs. Let's add another site in Hawaii. So once we add that site, we start to see these hints of a ring. But honestly, if this had been our image, I'm not sure what we would have said. It could be the base of a jet that's opening up. It could have been many things. But then we add our final site, and this is a site in Spain, and then the image sharpens up into this nice ring. So again, this is why it's so exciting to add, say, that next site in Greenland, and how is this image going to evolve? And the other really exciting thing about the sites in 2020 is that they bring short baselines. Short baselines see large-scale structure. So a question we get a lot is, we see this ring, there's this black hole here, where's the jet? At every other frequency anyone's ever done the LBI, they see a jet, big booming thing going off this way. Where is it in this image? And we don't have baselines that can see those scales. So this is one thing that will come in the future. So just tying this whole process together, this is the procedure for taking data. We have these incident waves, they're recorded on all the telescopes, and this is recording petabytes of data. So that data is then shipped to a correlator, which forms the pairs between all of them, and then it aligns them to some accuracy of femtoseconds before calculating these correlations. In calibration, we then do amplitude calibration as well. So we try to understand how much noise each detector had and use that to calibrate the absolute level of the signal. And then we feed it into all these different imaging algorithms, and these eventually turn into the final process. And in each stage here, we have an immense reduction of data. So at the beginning, it's petabytes. At the end, the information in this image, when it's compressed, is less than a kilobyte. The total number of measurements that go into this image are maybe a few hundred. So it's this beautiful process of trying to keep as much information in the signal as we can while reducing it many, many orders of magnitude in volume. Okay, so there's an image. What does it mean? So it turns out the easiest thing you can extract from this image is the mass of the black hole. And I just wanted to walk you through how we do that in a sort of cartoon way. So here's how it works. A black hole, we expect to cast this shadow on its background. And one way to think of what this shadow is it's the photon cross-section of a black hole. You can imagine, suppose it's backlit with plasma or something like that. It's going to punch out a hole in the middle of the image. And what we're interested in is what's the boundary of that hole. So it turns out this was worked out in 1916 by the mathematician David Hilbert in an article that he very modestly titled The Foundations of Physics. And so what he calculated was that the diameter of the shadow is square root of 27 times the Schwarzschild radius of the black hole, or the radius in terms of gravitational units of the black hole is about 5.2 times the gravitational radius of the black hole. So it turns out for M87, we think we know the mass of the black hole because we see stars orbiting around it. We don't see individual stars, but we can see their bulk motion. And this gives indications that the mass of the black hole was about 6.6 billion solar masses. So if you take that mass from stellar dynamics, it would predict a shadow that's about 40 microarcseconds across. Now, black holes have more than just mass, but not much more. It turns out the only other degree of freedom an astrophysical black hole has is that it can be spinning. And it turns out that spinning black holes cast a different shadow. But the amazing thing is that spinning black holes have even when they're almost maximally spinning, they'll have almost identical shadows to non-spinning black holes. So it turns out this inner ring is what you would see if you're looking at a black hole down the barrel. So this thing's spinning up to its maximal amount, and down the barrel, it only shrinks by about 8% in size. And the special thing is that that's the full range of possibilities for a standard, or what's called a Kerr black hole. If GR is correct and black holes are what we think they are, the shadow would have to lie in this tiny range. So this is special because it means that we have this beautiful way to test whether GR is correct. But it's bad because it means that our measurements aren't going to have very much of a handle on spin, right? It's not that the spin of the black hole stretches this or something like that.
Question?
Yeah.
So this shadow that is cast by the black hole is independent on the rotation axis?
It's not.
It
turns out that this is the smallest that it could possibly be if you're looking at an edge-on, or if you're looking at face-on. If you look at an edge-on, it'll it won't be a circle anymore. It gets pushed a little on one side, but it will live within this range. Yeah. Okay, so now the problem for M87 is that there are other ways of estimating the mass, and these don't agree with the stellar dynamics. So you can also estimate the mass using gas dynamics around the black hole, and these gave a different answer, about 3.5 billion solar masses. So the problem is, if we knew exactly what the mass was beforehand, we'd have this really tight test of GR, but here we have a factor of 2 uncertainty between these different methods. Now, just for fun, what about other types of objects? You know, maybe M87 isn't a black hole, right? Maybe it's a wormhole. So if M87 were a wormhole, and it had the mass from stellar dynamics, it turns out it'd be smaller. Wormholes have smaller shadows than black holes. A wormhole would have about the same size as this gas dynamical boring black hole, and maybe it doesn't have an event horizon. Okay, so it turns out that you can have these singularities that look like black holes from great distances, but they're not veiled behind this event horizon. They're called naked singularities, and it turns out that they cast much smaller shadows. So there are all these different predictions for what it could be. And you can put the EHT image behind those, and immediately we see that all of these possibilities are ruled out, except the case of this black hole with the stellar dynamical mass. And so that's why we think that this mass is about 6.5 billion solar masses. So this is us, trying to use this image to test GR. But we can also use our image then, assuming that GR is right, to try to estimate what the mass of the black hole is without using previous estimates. And there we use 3 different ways. One is that we're using our images and just try to calculate the diameter of the ring in these images. A second is using geometrical model fits to the data instead of imaging. And a third is actually fitting numerical simulations of black holes. And these three points with uncertainties are the results from all of those, and you can see that they agree quite well. With about a 10% uncertainty.
Can I ask you something? I'm sorry.
Yes, please.
What do you mean by testing GR? Everything is consistent with GR, everything on the screen, correct?
That's right. So we have nothing that suggests that.
Yeah, what I'm not understanding is your statement, testing GR. Because all you do here is general relativity, just assumptions about the objects, different kind of objects.
So I guess I would categorize this as a null hypothesis test of GR, right? So if GR is correct, and if, say, the stellar dynamical mass is correct, you would expect a shadow of a particular diameter, and our results are consistent with that.
Well, the only thing I see here is actually identifying your object, but everything is consistent with GR, correct?
Well, I see, yeah, absolutely, yes.
Yeah, so it's not testing on GR, it's just finding out what kind of object you are observing.
I suppose there are different ways of interpreting this. If I saw an object that had a shadow that was twice as large as what was predicted by GR for a Kerr black hole.
If you break actually the slightly values, if it's not consistent with that formula, yes. But everything else.
No, okay, so then I would say, more precisely stated, this would be something like testing whether supermassive black holes, or the objects at the center of galaxies are Kerr black holes or something like that. Yeah, but even this, I would say, is a soft way of doing that.
Testing just hypothetical statements of other people who try actually to modify GR. So.
Well, we should talk more at the end. I mean, I think. Okay, yeah. I'll show some examples at the end, I think, that are more stringent tests. Okay, so we don't think that the black hole is this blurry blob. This is the limitations of our instrument. What we think it probably looks like is more like numerical simulations of black holes. So this is an example. There's a full 3-dimensional numerical simulation of the plasma being dragged around a rotating black hole. And so these can be simulated now, run for long periods of time. In this case, a second in the simulation is about 2 weeks in real time. So the question is, what information do our current EHT data provide about these types of simulations? How can we constrain them and learn about the actual physics that's happening near the event horizon? And there, it turns out the answer is we can't say much yet. So here's 3 examples of numerical simulations, and it turns out these are all perfectly consistent with the data that we have so far. Okay, but what's alarming is this one on the right or left, I guess, is a black hole that's spinning almost as fast as it can, but it's actually got a retrograde accretion disk. So the black hole is spinning in the opposite direction as the material is accreting onto it. In the middle, we have a case where the black hole is not spinning at all. And on the right, we have a case where it's prograde. So it's spinning fast and the accretion disk is going in the same direction. More than this, in this case, the magnetic fields are quite weak. That's what sane means. In this case, MAD stands for magnetically arrested disk. This guy has strong magnetic fields. And these are all perfectly consistent with our data. So we can't constrain the spin, we can't constrain the accretion rates, we can't constrain the magnetic fields. The black hole is completely dominating what we see here, right? It's just this, the curvature of the space-time that's creating a ring in the image no matter what you do. So one other example of this is sort of a basic diagnostic of these simulations is what the accretion rate onto the black hole is, right? So generally that tells you how much energy is being put out by the system. It's just based on how much mass is falling into the black hole. And the simulations that we've done that are consistent with the image we see differ in accretion rate by about 3 orders of magnitude. So clearly we have a lot to learn. And the only thing we really tightly constrain at this point is the mass of the black hole. So what might we do next that would break some of these degeneracies? So it turns out one thing we could do is study the polarization of the light. So it turns out EHT observations have reported full polarization every year since 2013. And so we should be able to make polarimetric images from the data that we already have. So on the top here is a magnetically arrested disk. So this is strong magnetic fields on the top, weak magnetic fields on the bottom. It turns out that these are both fully consistent with our current EHT observations. This is what we might see. This is convolved with a beam that's the same as the EHT. And this is convolved with an even smaller beam, something we might see with EHT in 5 years. So even in 5 years, we probably wouldn't be able to confidently distinguish between these two cases if we look at just the total flux. But if you put polarization on top of these, they look completely different. So in the magnetically arrested disk, you have these strong magnetic fields that lead to this, this sort of swirling pattern of polarization. And on the bottom, these weaker magnetic fields give just a completely tangled and chaotic picture. So this is something that even in the next year, we might be able to release images that break these degeneracies.
Talking about the polarization of the microwave that we received.
That's right, yeah. So this is synchrotron radiation, so the polarization is orthogonal to the magnetic fields. The other question here is the time variability. So here's an example. This is M87 on a slightly larger scale. So this is with the LBI at 7 millimeters, not 1 millimeter. And the cool thing here is that we actually have data taken over many months. So one thing we've been working on is new algorithms that take a series of data and don't reconstruct images of it, but actually reconstruct a movie. So here, I actually took 8 months of data, and we're just going to turn it into a single movie. And so you actually see that this jet is alive, right? It's writhing and injecting material into it. And there's the EHT image, and you shrink down the EHT image to its proper scale on this image. It actually sits right down in the heart there, where you see almost no structural information. So what we know is that this is a living system, and the black hole is anchoring it all. This dynamics will extend all the way down to the black hole itself. And a crucial question is, is this ejection of material being driven by this rotating black hole, right? Or is it happening further out in the accreting material? And to give a sense of why this is really a near-term thing for the EHT, it turns out we know that M87 was changing before our eyes in 2017. So we have observations. We had 4 nights of observations spanning 6 days. And it turns out if you look at the raw data, this is a quantity called closure phase. Okay, so closure phase is very special in that it doesn't have to be calibrated. It's a combination of data products that's immune to almost all types of sort of atmospheric or instrumental errors. And here you see on the days that are adjacent, the closure phase is almost the same. And on days that are separated, the closure phase changes a lot. So we know that this is intrinsic structural evolution of M87 over timescales of just 4 or 5 days. It's really exciting that as we complete the array, we're going to start to be watching it in real time. But with our current coverage, it turns out that we can't really associate any clear structural variability with these changes that we see in the data. So here on the first 2 days, you'll notice it's a little brighter up here on the upper left. And on the last 2 days, that seems to move. You see a little brighter on the bottom and the lower right. But it turns out that if you think, oh, that's a rotation, it's actually rotating the wrong direction. So the way that what we know is happening here is that it's brighter on the bottom because that's where material is flowing towards us. It's fainter on the top, that's where things are flowing away from us, things that are spinning. And this is a relativistic Doppler effect. And so we actually know the direction of rotation, and it's the opposite of this motion of this feature. So what we need is denser observations and really more baseline coverage to start to see how this variability is connected with the image structure. Okay, so I think you now have a sense of how we form these images and the things that we're confident in and maybe the things that we're not so confident in. So what's next? Like, what could we do that would make this so much better and really pin down all of these remaining uncertainties? How do we actually get to something like a precise test of GR, right? And go from this, which is just some donut on the sky, to something like a precision measurement of black holes or of the metric. And for that, it turns out there are some new ideas that are really promising. To understand them, you can look at this simulated image of M87. And here you see this ring. It's got a thickness of something like 1% or 2% of the ring diameter. And on the interior of the ring, you see this bright edge. Okay, so this is the photon ring of the black hole. This entire ring actually only has about 10 or 15% of the total flux of the image. Everything else is much fainter, but there's more of it. So this is actually already just a fifth to a tenth of what's sitting in the image. But that's the thing that's encoding GR, right? This thing, this bright inner edge, which carries almost no flux at all. The size and shape are where we could just read off what the mass and spin of the black hole are. But the problem is, to get that, we have to get to something like micro-arcsecond resolution. And these are effects that would be completely dwarfed by the astrophysics in this image, right? The stuff sitting inside the ring, stuff that's sitting outside the ring that's flowing onto it. So how can we isolate that picture of the ring? So to understand this, it's useful to zoom in on some profiles. So these are just slices across the image. And what you see is that it's not just some simple structure. What you have here is a series of bumps. Okay, and what that is that as the photons are going around the black hole, the longer they spend near the black hole, the more emission they pick up. It's brighter and brighter based on how many times photons loop around the black hole before coming to us. And it turns out that these bumps are basically counting up for us how many times photons orbited around the black hole. So to get it to orbit many, many times, you have to shoot it more and more closely to this bounding edge that defines the boundary of the black hole shadow. So if you zoom even further, here's one example just on this narrow range. You see all these different lumps that we can, when we break them apart of a number of times that the photon had to orbit, we see that they stack like layers in a wedding cake or something like that. Now, from an image perspective, accessing this information is hopeless. Like, these things have such a small amount of energy in the image, right? Even with this high resolution simulated image, it's hard to even see what's there. So it seems like it's a completely hopeless problem at getting this astrophysically. However, the beautiful thing about them is that because they're narrow, increasingly narrow, they're perfect to measure with an interferometer. So we've done all of this work to go from interferometric data to pictures. But it turns out to measure these subrings, and to precisely measure GR, what we want to do is we want to stay natively in the domain of the interferometer. We want to see the sky as an interferometer. Every baseline is just picking out one particular spatial frequency, remember? And it turns out that those spatial frequencies are very closely connected with the different rings. So here's an example. So this is the actual visibility response of an interferometer for the simulated image. So it's not a toy model, this is an actual three-dimensional simulation. Now the longest EHD baselines are living around here. And they're in this region where it's a very messy signal. It's dominated by the astrophysics. Once you go out to longer baselines, it turns out that the signal cleans up a lot, and it turns into just a very regular oscillating pattern. So it turns out that the red and the blue are those slices, horizontal and vertical. They're just baselines along those two different directions. The black on top of that is just a very simple model that I fitted that has 6 parameters. Now the strongest feature in these is of course the periodicity. And it turns out that the periodicity in these signals corresponds to the diameter of the ring along that direction. So one thing that you'll see here is that the diameters along the two directions are a little bit different, right? You can't see this with your eyes in the image. It'd be impossible to measure this with a realistic image reconstruction. But to an interferometer, you can actually just read it off, right? You see that the red is sliding to the right of the blue here. And so the fitted diameters in this case would be actually accurate enough to tell you what the spin, direction, and orientation of the black hole are. Because in this case, the spin is slightly distorting the image. Now it turns out if you go to longer baselines, you do even better. So it turns out this stack where it's indexing like layers in a wedding cake by the number of times the photon went around the black hole, these turn into this damped cascade in the visibility domain. So the EHT measurements, of course, they're sitting around here. It turns out if we went to extremely long baselines, we don't need a whole array. We don't need many baselines, lots of orientations. We could just take a single baseline at a very long length, maybe with a station on the moon or in L2, and that would get us to these higher order subrings that are precisely capturing the shadow properties, the diameter along different directions. So this is a way that we can actually get to this, the precision tests of GR, measuring the mass and spins of supermassive black holes and so forth, without needing to build 100 new telescopes. Maybe we just need one. So to summarize, the EHT is now capable of creating images of black holes, including the supermassive black hole in M87. Currently, we have a lot of confidence that we are seeing this supermassive black hole and that we know what its mass is to an accuracy of about 10% for the current EHT measurements. However, beyond that, it turns out that most of the astrophysics is still pretty poorly constrained by EHT data. Now, this is something that polarization images will certainly break a lot of degeneracies. They'll start telling us about how magnetic fields look near the black hole, how material is evolving, how much stuff is falling into the black hole. And in addition to that, the EHT has a lot of developments underway to add new telescopes to the array and also to push to even higher frequencies and improve the angular resolution. What I'm most excited about, though, is that maybe we can do better with just one long baseline. Maybe we go to space with a single dish, and that could be the pathway to precision tests of GR. This could then be coupled with a dense ground array. So the dense ground array would give you kind of the broad overall structure, and then you'd see this sharp photon ring with just 1 or 2 telescopes in space. Before I close, I just also want to emphasize this project is really a huge international team. It's got experts in engineering and instrumentation, theory, the modeling and so forth, and it really wouldn't be possible with all these different efforts. So it's a great group, and I'm so happy to share the results with you today. So thank you.
All right, we have time for questions.
Yeah, one regarding the frequency. So, why it helps so much increasing frequency, and it's very difficult to get into the terahertz regime just because of lack of instrumentation working on that regime, the terahertz class?
Terahertz is tricky. Terahertz, the Earth's atmosphere becomes optically thick, or it becomes opaque. So observing from the ground at terahertz frequencies, there's really only probably 3 or 4 sites in the world that are capable of that, and it'd be hard to get an array that has enough telescopes to do imaging. You can go to space and do terahertz observations. It's of course much more expensive, but also you would need extremely accurate atomic clocks. It turns out masers wouldn't be accurate enough to get you to terahertz. There are other types of atomic clocks that are better by a few orders of magnitude, but this is all cutting edge stuff.
But to synchronize the different.
That's right, to synchronize the different telescopes. There are other concepts. In space you could maybe drive them from the same clock. But again, these are multi-billion-dollar missions already. There's no easy path. As one example, one of the best sites in the world is in Hawaii. Well, you've probably heard about it from all the stuff about TMT, but there are sub-millimeter facilities on Mauna Kea. So Mauna Kea used to do observations only at 690 gigahertz, right? They didn't even go up to a terahertz. They canceled that because the number of nights a year just made it was too hard. So getting above 230 is really going to be tough, and that's why the possibility of doing some real science with only, say, 2 sites or 1 orbiter is really appealing to me.
Are there any telescopes in space right now that would be useful?
So it turns out that space interferometry is already being done. It was being done with a telescope called Radioastron. The problem with Radioastron, well, it actually just died. It was launched.
That's a problem.
But even if it was still working, it never observed above about 20 gigahertz. So it has to improve by a factor of 10 to join the EHT, and that requires a much better surface and all these other things. There are a number of telescopes that are being considered where they're planning on just launching as standalone facilities. So one of these is called the Origins telescope, and another is called Millimetron, and so forth. These are often not designed with interferometry in mind. So what we're trying to do now is to go to these planned missions and say, why don't you add on this little bit of extra instrumentation and then you can join the EHT. And I think now that we are really demonstrating you can make images, there's a lot of interest in that. So, I mean, there will be millimeter space field VI in a decade. It's just a question, I mean, how exactly to get there is not so clear though.
Yeah. If you put a telescope out in space, how would data transfer go? I mean, if you're working with that much data, can you even feasibly transfer that in a reasonable amount of time?
So the data rates that we're hoping for are something like 128 gigabits per second. And if I'd given a talk 3 years ago, I would have said, this is the reason you'll never do space field VI. So these are, 1,000 times the standard data rate at radio wavelengths. The breakthrough here is laser comm. So it turns out laser comm, you can transfer 100 gigabits per second easily from low Earth orbit, or even from well, they've already demonstrated 2 gigabits per second from the moon. Some of you may have heard of this SpaceX Starlink, right? We're going to put a blanket of these telescopes doing laser comm. So this is the kind of problem that 2 years ago was impossible, and 5 years from now will be trivial, right? And that's what's so exciting about this field, right? Is so much of it is tied to digital technology, and we just cannot fathom the rate at which this is developing. So yeah, the data rates that we have in mind, 2 years ago, unthinkable. Today, it's like, cutting edge. But I think, 10 years from now, it's just going to be completely standard equipment that broadcasts it down, and it's probably not even that expensive. Laser comm is extremely impressive.
Thank you.
Not to be greedy, but when are we getting Sagittarius A star?
Yes. Sagittarius star is my favorite. Well, I've spent most of my career on it, so I am very eager to publish. So for those who don't know, Sagittarius star is the supermassive black hole at our galactic center. We know much more about it, right? The uncertainty on the mass of M87 is a factor of 2. The uncertainty on the mass of Sagittarius star is less than 1%. We see individual stars orbiting around it. It's the perfect test bed. It's a little black hole, so it's about 4 million solar masses. M87 is about 6 billion, but it's also much closer. So it turns out they have about the same angular size on the sky. So why haven't we published it? Sagittarius star has 2 complications that are essentially unique among all sources ever studied with field VI. The first is that we're looking through the plane of the galaxy, and so we're looking through spiral arms that have a lot of ionized plasma. And at radio wavelengths, this is the same as basically looking through frosted glass. So it causes the image to be scattered and irregular. And so a lot of what we're doing is trying to develop techniques where we can try to invert the scattering, and they'll also make sure that if we're seeing effects, we know what of those effects are from the scattering and what might be intrinsic to the source. But the thing that's the real killer is the time variability. So in black holes, the mass of the black hole is the ruler for everything. It's for length scales, time scales, everything. So a day in the life of M87 is a minute in the life of Sagittarius star. We see these hints of variability over 6 days. That means on 6-minute intervals in Sagittarius star, our source is evolving. Innermost stable circular orbits around Sagittarius star are between 4 and 30 minutes. What this means is this technique that I told you, where we let the Earth rotate, we build up all this information, and then we reconstruct an image, doesn't work for Sagittarius star, right? That assumes that your source is static, and there's just no sources that have ever been studied with VLBI that are evolving so dramatically where you have to worry about this. So this is actually why we developed all this machinery for reconstructing movies, was to try to mitigate study the variability in Sagittarius star. And the problem here is that if you try to reconstruct a static image from Sagittarius star and it's moving, it's not that you just get back some time average blurry image. That's fine, we would have published it already. It's that it breaks all of your assumptions, you just get the wrong answer. So this is, so the good news is there's nothing wrong with the Sagittarius star data. We have a lot more of it than M87 actually, and probably better quality. It is coming, images are coming, and the time scale is months, not years, but it's a hard problem.
What about all the big black holes around there in other galaxies?
So M87 is one of the biggest inferred by any method in the universe, right? 6 billion solar masses is quite large for a black hole. There are hints of black holes, a few others that are maybe 3 or up to actually about 8 times the mass of M87. These are more speculative, and they're often much further away. So these are the biggest black holes. M87 and Sagittarius star are the biggest black holes on the sky as viewed from Earth. The next largest is M31, which is about a factor of 2 smaller. And then there are many others. It sort of grows like the cube of your resolution. So the issue there is, it's not just that we need the black hole to be big on the sky, which means a large mass to distance ratio. You also need it to be bright enough, right? You need it to be lit up in sub-millimeter wavelengths. And if you're looking at a system, it's got to be translucent, so you're able to look all the way to the heart and see the black hole. And you can see for M87, you have to go to pretty high frequencies to do that. So it requires sort of many different conditions all working fortuitously for you. But we actually observe about 15 sources. These aren't the only 2, and we do take all these candidates seriously. So there is a chance that there will be other black holes in the future, but probably to see, say, hundreds or thousands of black holes, you need, something orbiting at L2 around the moon or something like that.
Right. What? Okay, last question. Okay, sure.
So why does this one side is brighter and the one is dim? You said that the radiations are coming towards and away. So what is forcing to pick the directions for the radiation? So it's a very supermassive black hole and it has like its own power. Why does it pick a specific direction to, throw the radiation in one direction, and for the other side it's thrown in the other way?
Yeah, so in that zoom in, right, M87 has this long jet coming from one side. And if you think about it, what it looks like is the black hole spraying stuff out one side. It turns out that's sort of an illusion. We're actually looking at this black hole almost down the barrel. And what's happening is that the side where it's ejecting material towards us, it's much brighter. The side where the stuff is blowing away from us is much fainter. So there's actually jets going each direction, and we just see the one that's pointed towards us. As you get closer and closer to the black hole, though, the material's it hasn't had enough time to get accelerated in the jet. So this emission that we see, we actually don't know where this is coming from. This is one of those sources of uncertainty. It turns out this could be in the forward jet. It could actually be emitted from the counter jet, or it could be emitted from an accretion disk, and we don't have constraints on that yet. But this is something in very high resolution images at slightly longer wavelengths. You can actually see the faint start of this counter jet before it becomes too faint because material's just flying away from you. Yeah. But yeah.
Well, let's thank Dr. Johnson again for a lovely talk.